Abrar bhai, all are from corporate or academic or professors, like how it is?
It's a mix. It's a mix.
Mix.
Amir bhai, जी.
Okay, ठीक, fine. So this is what we are going to cover in today's agenda. Like we should know what is FPGA, and especially the concept, like what exactly the FPGA is, what are SoC, what do you mean by soft core, then what do you mean by hardcore processor, and with some applications like FPGA application, IoT, ADAS, and so many applications are there. So this is how we are going to start. So these are the some of the modules which is actually required if you want to grow in the industry with the recent, like you should know a basic electronic things like about devices and all. As you know that almost so many things are like internet of things, IoT devices and all. So basic electronic is very much important, then language is also important. I used to train on all this like modules, like controllers, so many controllers are there, processors are there, then DSP modules, Linux. So all these things are required. I will take it in like last career section. So then this is like a brief introduction about me. Like I worked as an application engineer with Crane Software International Limited. Then I switched to Starcom Information Technology as a product engineer. So where I worked with the Texas Instrument teams and all, with a different controller, processor and all. As I told that TI used to provide so many. It's a silicon manufacturing company, so used to provide so many different like innovation development boards, ICs and all. So then I worked as a assistant manager in FTD automation, where they used to work with ISRO, DRDO and all. And now I'm working as a consultant, you can say freelancer, with many companies in software development, hardware development, as well as I'm like you can say I'm into two different domains, like academic and corporate. I used to provide training for engineering colleges as well as corporate training for companies like yeah, this one you can say Collins Aerospace, L&T and all. Okay. So then we will start. This is about a brief about me. Even I was a evaluator for this the innovation challenge. Texas Instrument used to conduct every year the innovation challenge and all. Okay, where student make innovative products. We need to check like how they are innovative, what are the schematic diagrams, and how they made the prototype product and all. Okay, fine. That is all about me. So we will start with FPGA. So we see now, as you know, if you are student or even if you are a industrial person, so you have studied this already. You have studied this in your academic and all. But the thing is, what we learned in our academic is like okay, some executed some 10 programs or 20 programs. We designed this add and gate or gate marks, so many things. We have did a lot of things, because we have not spent 1 year or 2 year, we have spent 4 years in our engineering and all. So we have done so many things. Even if you take the example of controllers, we learned controller, we learned digital electronic, we learned analog electronic, so many subjects, like very interesting subject. But the thing is, the way we need to learn, we haven't done it. That's why we are struggling in our industries and all, because it's simple thing. Even most of the time when I ask for C developer and all, a basic thing, how you are going to store the value and how you are going to retrieve the value. So it is difficult to answer him, because only data type means int, char, float and all. But when it comes to understanding how you are going to store the data, when you say floating point, whether your processor or controller know whether floating point, what do you mean by that dot, whether the processor understand, whether your controller understand that dot, like you are going to store 3.1 and all. So how you are going to store the values, because these are very much important. We learned it, but we need to understand, because you see, when we know the concept on it is very easy for us. Okay, so we'll start with FPGA. So today we are going to learn about FPGA. We are not into more into technical and all, but we are into more concept understanding way. So FPGA, what do you mean by FPGA? Everyone knows that the term FPGA stand for field programmable gate array. Okay, that means you can say FPGA is a chip, IC. It's an IC, it's a semiconductor chip. So where you are going to design. So most of the time when you ask like what do you mean by FPGA, FPGA is something where we can design our own architecture. That means we can design any kind of system on our FPGAs. Like we can design digital circuit, PLDs. It's like similar to your PLDs, FPGA. So PLDs are nothing but a programmable logic device. Okay, but the disadvantage of PLDs are it is limited to some hundreds of gates and all. But if you consider, if you see the FPGAs, so it will support thousands of gates, so you can say now millions. So it's like under process so many things they are doing improvements on FPGA. They are using DSP into FPGA, they are using embedded system, you can say ARM Cortex into FPGA, and still they are working on that power. That is what disadvantage, so many pins are there, so even they are working on that also. So you can say FPGA is nothing but a programmable gate array. We can program that IC. That means we can design any kind of system. So what we need for that, see, even if you take the example of your controller, or even you can take example of your, yeah, please be unmute other people. Okay. So the thing is, so what we need, if you see, this is a hardware, na? Whether it's a controller, or you can say a processor, or you can say a FPGA. So these are the hardware. Hardware in the sense these are dead guys. Dead guys means they won't work on their own. We need to give some commands for them. If you take the microcontroller, even if you want to blink an LED, or you want to turn on the LED, so what you directly your controller will not turn on that LED. You should tell them, you should give some commands. So that, okay, please, a controller turn on the LED. So how you are going to give that commands? Okay, so you can give that command through some languages. That is how we are communicating with each other. Like so many different languages are there. English is there, Kannada, Tamil, Telugu, Malayalam, Gujarati, so many different languages are there. So what we need is we need to learn some languages where we can talk with our devices. Like we are learning English. Why we are learning English? Because we want to talk with world, because it's a universal language. But if you know Hindi, we can survive in India. If you know Kannada, we can survive in Karnataka. That is how the language, that is exchanging the information and getting our work done. Similarly, when we talk about hardwares and all, so what we need to learn some language where we can talk with the devices. So there are so many different languages, programming language, like C is there, C++ is there, Java, then Python. So many different languages are there, right? So why we need these languages? To talk with the devices, to make, to give the command to the devices. Getting my point? So I want to turn on the LED, so I will give the command by reading the instruction sets and all. I will program accordingly. Okay, by reading the architecture, by reading the pin diagrams and all. Getting my point? Where you write the embedded C program, how you will write the embedded C program? By understanding the architecture. If you don't know the architecture, you can't write a C program for that controller. You should learn where I am writing, whether I am writing for 8051, whether I am writing for PIC, whether I am writing for ARM, whether I am writing for some MSP 430 low power controller, whether I am writing. See, you need to know the architecture, then only you can write a code. So yeah, the thing is here language is very much important. Similarly, when it comes to FPGA and all, we should also know some language, but here it is different. Here you can say it's a HDL language what we are using in FPGAs. HDL means hardware description language. What do you mean by hardware description language? Hardware, we are designing the hardware here. We are not writing a code for ready-made architecture. We are designing our own hardware. That is what we say here. We can design any kind of system on our FPGAs. Okay, so you can see this any kind, in the sense I can connect this FPGA to my monitor. I can make a program in a such a way that I can connect to my monitor having a VGA port or HDMI port or DVI-D port, whatever you want. I can have a communication between this. I can have a communication with the keyboard. I can have a communication with the USB. So many. I can design this chipset. I can design this hardware according to my wish and will. Okay, so that is where I am telling that FPGA is something where I can design any kind of system. So let's go try to understand some background about how exactly these things came. As we know that so many invention is happening from last centuries and all. So it started from transistor. As you know that previously we used to have vacuum tubes and all. So even if you see the system computer. It is a huge full room size computer is there. So but now it is reduced to a mobile phone. Are you getting my point? So many innovation happens. So there is an innovation in your electronic industry, n number of controller, n number of processor. And if you see that, as I told, that at Bell Laboratory 1947 they did a research on that physics of solids, and that they replaced that vacuum tubes to some ICs, like you can say microprocessor. So if you see, the first IC was invented by Intel, that is what, a 4-bit micro processor, that is in the year 1971. If you see this, this microprocessor, see, it is again same microprocessor or microcontroller or any IC, it is again same. So these are made up of n number of transistors. So that is what already we studied in our academic. The transistor, n number of transistor act like a switch. So with that help of switch I can design any system. That is what, not so digital, what your devices understand. They understand only binary language, that is what, zeros and one. Apart from that they don't know A, they don't know B, they don't know C. Getting my point? All those things are achieved with the help of your transistor. As you see that in 1971 the Intel have like 2300 transistors within that chip. And if you see that speed, if you see that speed, the speed of that is was it is a 108 kilohertz. Are you getting my point? The clock frequency, where 1 kilohertz. So what do you mean by this kilohertz? That is also important. Clock, see, we learned clock, but we need to understand clock also. The clock is used for what? Instruction, executing the instructions. So we need is, here you can see that kilohertz, that means 108 kilobits per second. So that number of bits executed per second. Fine. So then as I told, that microprocessor came, Intel developed, so many innovation happened, so many different processor came into market, so many controllers are there. But if you see all this microprocessor controller and all, this is what a fixed set of architecture, fixed set of instructions are required, because it is designed by some company, whether it is a designed by AMD or it is designed by Intel or it is designed by some NXP, or different companies are there. Okay, so what they have done, they have designed their own architecture, and it is fixed. What we need to do, if you want to work with those architecture, so what we have to do is, we need to learn that data sheet, we need to write a code according to their architecture. And here it is a fixed, they have given some fixed set of instructions, set of instruction in the sense the commands. Getting my point? We learned assembly language, right? In assembly language, so many set of instructions are there, like move is there, accumulator is there. You are doing that assembly program, now move A comma B. So many sets of instruction for addition, multiplication, so many things are there. So it is like we are reading those instruction sets, and according to that we are writing the code in assembly. And when it comes to C programming, then again we have compilers and all, where they used to convert. All those things will be there in this. But the main intention is, what I am trying to explain you guys is, these are all fixed architecture. But what we need is reprogrammable. Reprogrammable in the sense, we can program, we can redesign. So there are so many different reprogrammable devices are available. So that is, if you see that reprogrammable devices, like you have something called as a PROM, then something called as a PLD, then you have a FPGA. These all are what? Programmable logic device. That means it is not fixed architecture. You can design your own architecture. You can design your own RAM, your own ROM, you can design your own processor, you can design your own timer, counter, you can design any digital circuit. Getting my point? So that is what we need to understand, a reprogrammable. What is the difference between a fixed set of instruction devices and a reprogrammable devices? We will see, like, what do you mean by reprogrammable device, because FPGA is also reprogrammable, right? That is, we need to understand what do you mean by that reprogrammable, how we are reprogramming it. Okay, next, if you see this reprogrammable, that is a PLD. As I told that PLD is what? Programmable logic does. Again you can see this programmable logic. These all are programmable logic devices. PROM, then programmable array logic, programmable logic array. So what is that? That is nothing but we are using some like set of AND gate. You can see we have arrays of AND gate, we have arrays of OR gate. So what PLD include? It includes arrays of AND gate, or you can say arrays of OR gate. So how we are programming? We are programming based on our Boolean expressions and all. So what we can do is, we can have the information, and we can accordingly, what we can do, we can put that information onto our devices. Based on that, we can control, we can design our own system. Okay, so how we are programming this? We are programming this devices, or you can say ICs, electrically, by implementing our Boolean, you can say Boolean expressions. Like I want this, with the help of this truth table, I will have some expressions. So those expressions are dumped, you can, are programmed to your ICs. So what is programming? Programming is nothing but having some information. You are entering some information to your device. That is C program. You are entering some instructions in the form of binary to your hardware controller. Similarly, here also, what you are having that information with the help of that Boolean function and all, you are dumping those information onto your IC. That is what you are going to program. And here programming, in the sense, as I told, that processor as well as FPGA, these both are different. Your controller, your that microcontroller, what I explained earlier. So that is what, where we are doing software programming. We are writing some software programming. But when it comes to programmable logic devices like FPGA, PAL, PLA, PROM and all, we are not designing the software. We are not writing a software. We are writing the code for your hardware designing. That is called as a, the programming here, it refers as a hardware programming. Fine, we will see one by one. What is PROM? So as I told, that it is a array of, you can say array of AND gate, and it is a combination of array of AND gates, and it is a combination of array of your OR gates. So you can see, if you see your programmable read only memory. So if you see this block diagram, so you can see here you have a fixed set of AND arrays. But here, if you see here, you have a programmable. You can program here, but you can't program. It is a fixed. So here the inputs are fixed here. Input of, like you can say, whenever you give the input to the AND gate, the output will be fixed. The input to your array, or gates are fixed. Okay, so we will understand this with the help of one more diagram. You can see this is a good example. You can easily understand. Fixed in the sense, as I told, that if you take the example here, so here you have something called as a 3:8 decoder. So you have 3 input, and how many outputs you have? 2:3. That is what outputs you have. Okay, and here you can see that this input you can't change. The n number of input like x, y and z, this is fixed input. Okay, what was I was telling here? Fixed input, fixed AND array. So AND arrays are like, you can see the arrays, the design of the your decoder and all, it is like this. So arrays are what? It is a AND arrays, like you can see, these are the fixed input. But when it comes to your this one, what you can say, OR, you can say OR, as I told us, OR is a programmable means, you can see this X mark, X, the symbol X is used for your programmable connection. That means you can change this connection. So if you see the output of your A, that is what, it is a sum of min terms. Min terms is nothing but this M0, M1, M2, M3, M4, M5, M6, M7. These all are like your min terms. So how you can select? So this is your OR gate. So if you see this example, for example, we have two function, Boolean function, like for one for A and another for B. What is the Boolean function? Even we have learned this in our academic also, am I right? So we have learned this expression, we have done some theorems, so many things. But the thing is, we need to understand what exactly it is, how it is going to work. So if you see this example, the A, what is the output of A? The output of A is nothing but a summation of, you can see, 5, 6 and 7. That means min term, you can see 5, 6 and 7. So what is this? I will connect this, and this is programmable. X is nothing but, if it is a X symbol, programmable. I can remove, I can connect. This is a programmable to your programming language. So here you can see the output of A is what? It is connected to M7, M6 and M5. That is what summation of. It is a summation of M5, M6 and M7. Similarly, when it comes to B, you can see the summation here. It's a summation of 3, 5, 6 and 7. So you need to program, like it is connected to 7, it is connected to 6, it is connected to 5, it is connected to 3. This is how. That means your input is fixed. What I told, in your PROM, your input, that is what, AND array, your AND arrays are fixed, you can't change. But what you can do, you can program the OR arrays. The AND arrays are fixed, but you can program, what you can program, you can program your OR arrays. Getting my point? This is how the this one, what you can say, PROM, programmable device, that is PROM. Okay. So next, coming to this one, PAL. What is PAL? Again, it's this is also it's a one type of PLD, programmable logic device. So here, even if you see this block diagram, you have two things. It's an array of, you can say, AND gates, and here array of OR gate. But here it is different comparing to the previous slide. So AND was fixed and OR array was programmable, but this is different. Here you can see AND array is programmable, but your OR array is fixed. That means what? That means like you can program this inputs. Okay, you can see here, you can program this input. Getting my point? You can program the input, but output is a what? The output will be fixed. Getting my point? So this, if you want to understand, you can see here. So you can see here, there are two things here. As I told, that X symbol is used to represent what? X symbol is used to represent, so I can program this connection. It's a programmable connection. But here there is one more thing here, is it is dot. Can you see this dots and all? So this dot indicate it is a fixed, so you can't program this. That is what here is telling. I can program the AND array, but programming OR array is what? It is fixed. That is not the case here. Here is different. AND was fixed and OR, here this was fixed, but here this was like variable, programmable. You can see programmable. I can program this, I can change according to my requirement. But here it is different. This side is your OR array gates, or gates array, you can say array of OR gates. These connections are fixed, but here you can program this. So what is the output? It is a sum of product form. That is what AND gate is, a product, and a sum of, you can say it is a product form. And if you see the boolean function, what is the output for A? So you can see that. See, you can, by seeing here itself, we can identify what is the output for A. The output for A is what? It is, you can say X, you can say Y, X and Y. Then next is what? You can say it is X and it is Z dash, and you can say complement of Z. So that is what the boolean expression, boolean function, X, Y and X, Z dash, that is a Z bar. So you can say X, Y, X, complement of Z. That is what? Complement of Z. That is how it is designed. Similarly, if you see here, same thing. If you see, only two connections are here. There is a fixed, and where it is going to a programmable input. Like here I am giving expression as X and expression as a complement of Y. You can see is X and complement of Y. That is a product output. One is that output. The another output what I am getting here is this one. So what is this? This is Y. Okay, and this is Z, complement of Z, complement. Then what I am doing, these two input as well as this, I am ORing it. Are you getting my point? The product of this and the product of this, I am adding. That's why I'm telling that the output of this is sum of, you can say sum of, that is addition of sum of products and all. Getting my point? That is how I'm telling that programmable device. It is not fixed. I can program, as you studied in your academic, using a NAND gate or NOR gate. It's a universal gates, right? Like you can program anything from those gates. Okay, so programmable. That is what? Programmable. Fine. Okay. So next is what? PLA. So this is programmable array logic, PAL, and this is PLA, programmable logic array. And if you see here the difference, so you have array set of like AND arrays, and you can have set of OR arrays, but the advantage is that here both is programmable, whereas in this one, PLA, AND was programmable but OR was not programmable. But when you see this, and was fixed or was programmable. But this guy is having the advantage of both. You can see this is having both advantage. It's a having a programmable and array as well as a programmable or array. So you can have both programmable and array as well as or array. Okay, this is you can see it's you can understand this with the help of again the same as I told that you can see here. So you can see this is your what, a programmable or array, and if you see this is a programmable and array. Getting my point? So the symbols also you can see that x symbol is there. X means what? X represent what? X represent, okay, here you can see x represent what? X represent programmable, that I can program. So in the previous was this was programmable x, but this is dot, this is not programmable, it is a fixed, you can't program here. Okay, but if you see here, so you can program either this as well as this one. So that is what it is a you can say you can have a both programmable array, and the output is also you can say sum of product. So you can see here x y same expression what I explained earlier. So you can do the programming here also. I hope you understood what you mean by programming. Next, the main thing is FPGA. See why I told you that is also PLDs. Getting my point? Programmable means I can change, I can design my own architecture. It's not like your controller fixed architecture. Getting my point? In controller it is a fixed architecture. We are reading the architecture, we are understanding the instruction set, then accordingly we are writing the code. But here we are designing our own architecture. Getting my point? We are designing our own architecture. So it is not like user function. So you can say this, I can design my own functionality. It's not like just having one architecture and some application we will run on the it's not like that. I can design my own architecture. And if you see what is available, like what are the FPGA consists of, it is consisting of, you can say configurable flash memory, then you have IOs, then you have a logic blocks, then you have a routing. So it's a mixes of all these things. So you have a flash memory on your FPGA, you have IO pins on your FPGA, you have a logic blocks, that is CLVs, configurable logic blocks on your FPGA, then you have routing, your reconfigurable you can say interconnection between your different CLBs or from IOs to CLB and all. So this is what all those things are present in your FPGA. So as I told, reconfigurable, right? So this is what FPGA. It is a Spartan FPGA which belongs to a Xilinx company. Okay, when I say reconfigurable, so this is the IC. I can design this IC. I want a timer. I can design it. No, I don't want a timer now. I want to erase that. I want to erase the program, then I want to design my FR filter. No, I don't want FR filter. I will erase the code. I want to design some 48 cross 48 multipliers. I can design here. I can erase this. Okay, but the same thing, you can dump the code in your controller. You can erase. You can reprogram. But there you are programming based on fixed architecture. But here what you are doing, you are changing the architecture itself. You are reprogramming it. You are changing the design and all. You are making your own architecture. So how this is possible? This is possible with the help of your HDL code. Am I right? So what you are doing, you are writing a HDL code. It's a hardware description language where you are designing the complete architecture with the help of your gates like AND gate, OR gate, NOR gate, whatever gates are available. It's a digital electronics, right? Digital. See, digital electronics subject is very much important if you are designing some FPGAs and all. So all concept you need to learn if you want to become a IC designer and all. At that time you need to learn, or you should be a very good, you should be a strong at your digital electronic, because so all those things will come there only. So here what you can do, you can write that code in the HDL language, that hardware description language, then you can synthesize the code. Based on the synthesizes, what synthesizes will do, he will produce some schematics and all. With that schematic you will generate some bit stream, and then you dump onto your control, you can say FPGAs. Okay, then what you can do, you can start working on your FPGA. That is what reconfigurable. Okay, I can design any architecture, like timer I can design, filter I can design, counter I can design, I can design I2C protocol. Inside this I can design SPI, I can design UART, I can design USB. It's my own, based on my own requirement I can design the chip. I can design my I can design a ARM Cortex controller. I can make this FPGA as a controller. I can make this FPGA Arduino board. You are using Arduino board, you are using Raspberry Pi, this one, because nowadays most of the students, they are doing their project on these boards. Even you can design those architecture here. Getting my point? So we can design whatever architecture, whether it is a 8051, whether it is a PIC, whether it is a DSP, whether it is a ARM based processor. You can design your own architecture on this FPGA. That is where we are calling them as a reconfigurable PLDs, programmable logic device. Okay. So as I told that, if you want to understand FPGA, the best you can compare with your controller, as I was telling earlier, right? So you can see this. Okay, you can see this architecture of your FPGA and your architecture of your controller. So see the differences. What is the difference between your microcontroller as well as FPGA? So as I told earlier, if you want to understand this, you can take the example of your plot and flat. So what you can see, you can see the difference, right? What is the plot? Plot is nothing but some space, some area is there, which is we can build whatever we want. We can design our own architecture here. I can design a single bedroom, I can design a 2-bedroom house, I can design a 3 BHK flat, I can design an apartment of, like you can say, some 20 floor building, 30 floor building I can design. So this is what I have. It's a free area. Getting my point? It's like plot where I can design my own architecture. Okay, but when you see a controller is something like ready-made flats. So ready-made flat in the sense, you have a, like if you are going to buy a flat, so you will see that 3 BHK flat I want to buy in some good location and all. So what you will go and you will see your requirements might be n number of things, but the thing is, you are going and you are seeing that, okay, one bedroom is there, 2 bedroom, one hall is there, one kitchen is there, some 3 bedrooms are there. Okay, some okay, so many, swimming pool is there, so many things are there, but the thing is, it is fixed. You can't change it. Getting my point? You can't change this. But here, if you buy a plot and all, you can design your own architecture that is according to your wish and will. Getting my point? You here, you can't change. If you are in this floor, you can't change your architecture, because if you want to change here, you will disturb to other floors also. There might be chances of getting collapsed. So but here you can design your architecture, demolish, you can design, demolish, you can design, demolish. That is what I'm trying to explain you, what is FPGA and controller. So if you see the controller and all, so already we are seeing now block diagram, architecture and all, we are studying it. We are studying the architecture. Okay, processor is there, the speed of processor is this. Okay, timer, so many timers are there, 2 timers are there, 3 timers are there. Okay, interrupt controller is there, parallel ports are there, serial communication protocol, like as I told, that I2C is there, SPI is there, UART is there, some memories are there, RAM, ROM, GPIO ports, all things are like readily available on your architecture, because this is designed by some manufacturers. Getting my point? So but when it comes to your this one, you can say FPGA, so nothing is available, only some 3 blocks, like you can say logic blocks, interconnection, then IO cells. So with the help of some interconnection and all, you can connect, you can make with the help of gates and all. As I told, that you can design your own, you can design this architecture into this FPGAs. That is what I say, the reconfigurable means I can design my own architecture. I can design timer, I can design counter, I can design RAM, I can design ROM, memories. I can write my own instruction set, because you are using some, if you see the difference, 8086 is having a different instruction set, 8051 is having a different instruction set. That means number of registers are different, the size, the bit you have seen, no? So many variants of controllers are there, like 8-bit controller is there, then you have a 16-bit controller, 32-bit, 64-bit processor, so many others. So you can design your own architecture, you can design your own architecture. That's why I'm telling that FPGA is a reconfigurable. I can design my own architecture. Okay, then so to understand this, as I told, that if you want to understand still more like what exactly, so you can see your digital trainer kit. Can you see this digital trainer kit in your academic and all, or else in some companies also they are using for testing and all, but the devices will be different. So before doing this, they will make some schematic, they will do testing and all. So this is the digital IC trainer kit, where you can see you have so many slots here. Can you see this? So what we can do, we have so many ICs na? In our academic, we have learned so many ICs like AND gate, OR gate, NOT gate. The AND gate IC is 7408, the OR gate IC is 7432, and NOT gate 7404. So like so many ICs, you can say this is the logic, and this is the inside the IC, and this is the IC. This IC, what we are doing is we are inserting here, and we have some IO pins here. So based on that IO pins, what I can do is I can design my NOT gate, I can design my AND gate, I can design NAND, or and with the combination of this, as you told that some, as I told that NOR gate, using NOR gate I can design NOT gate, using NOR gate I can design AND gate, using NOR gate I can design NAND gate, NOR gate, because it is a universal. Using this gate I can design any of these gates. Getting my point? There is where we are doing a rig up and all. If you see that symbols and names and all, and even you can see the boolean expression, like what is the boolean expression for your you can say this AND gate. So AND gate is what? X into B. So what you can do is you are using this gate and two inputs, you are connecting two input to your supply, and one output, you are connecting one output to the LED. Getting my point? Then you are seeing the, okay, if I give 0 0, what is the truth table for AND? If it is 0 0, the output is 0. If it is 1 0, the output is 0. If it is 0 1, the output is 0. If it is 1 1, the output is 1. So you are designing this, you are testing this. Getting my point? So this is also programmable. This is a programmable kit. You can design your own circuit, right? Programmable means what? What I told. You can reconfigure, you can redesign. So I can, by having these pins and all, I can redesign it. Okay, so by having this I can redesign this. Okay, are you getting my point? What I'm trying to explain you guys, reprogrammable means what? I can design, I can reprogram. See, this is the logic. You see what you have done here is, it is not like just you made some input, you have given some input and you took some output and all. This is not actually, if you learn this in depth through concept and all, these are very interesting subject. This is all we are going to use in where, in our FPGAs. Getting my point? At the end, whenever you, if you build any big circuit and all, at the end it will come to this adder, half adder, full adder, multiplier. Getting my point? So it will be this is what you can say digital IC trainer kit. What you are learning in your academic, that is what you are designing, you are redesigning by having n number of ICs and all. Getting my point? Fine, you can see that I want to design half adder now. So I have a trainer kit, so I want to design a half adder. What I will do, I will take one IC. So what is there? First the thing is schematic realization. What is there? The circuit. What is the circuit? I need some two ICs. Am I right? One is for XOR, another is a AND gate. So I want a two IC. So what I will do, I will connect one IC here and one more IC here. Then what I will do, I will rig up the circuit. So what I will do, I will connect the inputs. Okay, from AND gate and OR gate to A, and AND gate OR gate to B. Some switches, some voltages we are giving here, right? So then next is what? Output. Output is what? Sum, or you can say carry. That what, where we are giving to some LEDs. And how we are watching, how we are seeing this result? We are seeing this result like A, B, sum, carry. If both are 0, the output is 0, 1. So that is how we are adding it. If 1 1 we have added, but we got one carry. So this is output. What, how you are seeing the output? You are seeing in the form of digital on your LEDs and all. Getting my point? This is how you are designing by using two IC. You have designed the half adder. Similarly, by using IC you can design full adder, you can design multiplier, you can design mux. So many things are there. You can design n number, because this is a reconfigurable. So you can see that, what you can say, even you can say your IC trainer kit is what? The IC trainer kit is a programmable device. Am I right? So many ICs options are there. with the help of I will put ICs at different location. I will take the input, I will take the output and all. I can create AND gate with this trainer kit. I can develop XOR gate. I can create a half adder, full adder, 2:1 max. So many things I can do. That's why I'm telling that IC is a trainer kit. It's a trainer kit is a programmable devices. Okay. If you want to understand a FPGA, you can see that FPGA in simple term is a super scale version of your digital trainer kit. Getting my point? Because at the end you are going to design some system. So you can say if your trainer kit, see so many ICs, you just you can what you can imagine that 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Some 12 ICs are there. With the help of these 12 ICs, what all design you can make, if you go back to your syllabus and all, n number of designs. Getting my point? But this is just, you can say it's a drop. But what FPGA is? FPGA is a ocean. Getting? So now similarly you say that how much time it will take. If you say, if you see this as I told, half adder, how much time it will take for me to do a half adder with my trainer kit. This is my trainer kit, right? If I want to design this half adder with the trainer kit, how much time? It will take 5 minutes. Am I right? Because input, you're gonna connecting input, two inputs, you're connecting to the switch, and two outputs you're connecting. Then you're taking here from here two input or connecting one output. Then you need one more XOR from output of similarly input from here to here, here to here. Then this output is connected to one. You are designing. It will take some 5 minutes. Okay, how many ICs? Two ICs. That's okay. And even as I told that NOR gate and NAND gate, these are the universal gate. Not only this, you can design with a NAND gate. You can design half adder using NAND gate. You can design half adder using OR gate. That is what I'm telling. You can make n number of circuit. That's why it is a programmable. Getting? So hardly for building a half adder, it took me 5 minutes and some two ICs. Okay, next we will go. Suppose I want to make a full adder. Can you see this full adder? So full adder. What is full adder? So you can see half adder. I made this full adder. I want like two half adder. I can you have done this in your academic, but the thing is understanding is important. You made this with what? Two half adders. Can you see this diagram? Half adder and half adder. What you are doing is you have some three inputs like A, B, C, and then you have some output. Then this is given to your next another half adder. You can see output sum of this one is given, and then carry is generated, and one more gate you are using here. So can you see how many ICs you need here? If you see this, one is AND gate you need, one is XOR gate you need, one is what OR gate you need. Am I right? Some three ICs are required here. But how much time? Because it took 5 minutes to rig up, like design this circuit and have experiment. But when it comes to this, it took some more time. You can say like two half adder I will take approximately like 10 minutes. It took me 10 minutes to design this circuit and test okay, testing this. I will give input and I will see the output. Okay, it's working fine and all. Okay, I have designed it. Fine. Next, suppose I want to design a 4-bit adder, because this is a digital, right? So I want to design a 4-bit adder. At that time, what I will do, I will use some full adders, like 4 full adders, 1, 2, 3, and 4. Okay, then I will use some inputs, A0, A1, A2, A3. That is what A input. It's a 4-bit, right? 4-bit adder. I want to add two 4 bits. Then I have the second input like B0, B1, B2, B3. You can see second input. Then what is the result? The result is what? S0, S1, S2, and S3. That is what? And with a carry, I will get a carry flag also. Or else, even if you have seen, you can have that input carry, output carry, and you can say input. So this is how I will design this. So how much time it will take by using this your trainer kit and all. Getting my point? I have a trainer kit, I have ICs and all. So it took me 5 minutes for half adder. It took me you can say 10 minutes for this one, what you can say, full adder. Then you are seeing now it will take almost, it will take, because you are designing half adder, then you are designing full adder, then connecting from this full adder to this full adder, this full adder to this one. You are getting my point? So approximately it will take some 30 minutes to 1 hour for you to design your own circuit. Getting my point? Fine. So if you go to a big circuits, Getting my point. Circuit in the sense, what you can say is like multiplier. I want to previously it was adder, right? So I want to design a multiplier like 4 cross 4 bit multiplier. Then you have seen, you're gone here. Okay, you need AND gate, full adders, so many full adders. Okay, from this to this to this, blah blah blah. Are you getting my point? Yeah, yeah, you can do this, you can do this. See, uh, this is also important, na? How many ICs, whether your trainer kit will support 10 ICs or your trainer kit will support 25 ICs. You need to take care of all about this. Okay, how many ICs is going to support? Getting my point? So it is too difficult. It is now it went from 5 minutes to 10 minutes, then to half an hour. It's taking me 3 to 4 hours. But the thing is, if you do mistakes, so many bugs, and if you see this difference, see this image I took from PCB designing. PCB designing is also similar, right? So with the help of like that schematic diagram on a breadboard, connecting so many wires. Can you see this huge number of wires? Oh, one pin is gone, so VCC is connected to ground, VCC is connected to somewhere else, dhab, your IC is gone. It's so confusing, am I right? So n number of this one circuits, like as I told, that if you are designing a board, a development board, you have IC. With the help with that IC, you have onboard peripheral. On chip peripherals are like RAM, ROM, and all what I told. Peripherals, IO ports, controller. But when it comes to your onboard peripherals, like you have a stepper motor driver IC, you have a LCDs, a 7 segment, hex keypad. So many things will come. But when I connect from my controller to those, so it will be like I am gone mad here, because if one wire is missing or short circuit, my whole project is gone. Am I right? So it will take huge time to fix the bugs, connect the wiring, testing, and all those things. That's why the PCB came into picture, right? So PCB designing. So what they have done, with they have drawn, they have generated some Gerber files, they have put it on your board, and you have connection. You just plug your IC, it will work. Similarly, here also you are designing FPGA, you are designing through your trainer kit. So if you are connecting from this pin to this pin, this pin to, if it is looking like this, then you are gone. So it is just, I'm telling, 3 to 4 hours if you are expert. But if you are starter and all, then you are gone. Fix bugs, so many things will come. Getting my point? Testing is also difficult. So many challenges will come here. Okay, so then if you want to design, see, this is just a 4-bit multiplier I told. It's so complex and all. Can you see this? It is so complex to design a 4-bit multiplier. But if I ask to design a 48 cross 48 multiplier on your trainer kit and all, because it is a programmable kit, right? So it's possible or not, I don't know. Like you have seen, na? So you need to have a number of kit. It is a single kit, right? So this is not sufficient. You need to have so many. So all the kids from different classrooms, or all you'll gather. You need to have so resources for that to connection and all. And you think that how much time it will take, and bug fixing gone for 4-bit adder itself. We are gone mad here. But multiplier, it's gone. Then fixing bug if some error is there, and reconnecting of that circuit and all. So it is very difficult. But early days people used to do that. As I told, that computer, big computer. Nowadays if a computer is getting stuck or getting heated, we will get into tens. But early days people used to do that, a full size home size computer, and the connection and all. But it's have lot of effort. So now, but now through doing this is through human, like human, you can say. But now humanly impossible to do this all things. Getting my point? So what is the solution to design our circuit? The solution is FPGA. Getting my point? FPGA. How in FPGA? Through hardware description language. So here, instead of doing all this circuit connection, this, that, and all, what I will do, I will write a simple HDL code here. Okay. So if you want to do what you can take, I want to do and, what I will write, C is equal to A and B. So what I will write a code, one line code I will write for AND gate, C is equal to A and B in my HDL code. So with the help of your synthesis tool and all, they will generate a netlist, and they will design the schematic. They can design a circuit, just a single line. You can design this half adder, full adder, multiplier. Getting my point? It is so easy. So that is where the FPGA came into picture. That is where we are telling that the FPGA is a reconfigurable device. You can say a reconfigurable IC. Got it? What I am trying to explain you guys, because we need to understand FPGA, because without understanding, simply writing code blah 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 and getting some result, that is not important. Getting my point? You will get 100,000 number of code from, if you go to YouTube, if you go to Google, ready-made codes, working codes are available. What you are doing, you are dumping the code, executing, oh, got the result, happy happy happy. That is not the thing. You need to know, you need to understand the concept, you need to understand what exactly FPGA, what is the power of FPGA, what we can do with that FPGA. Getting my points? Just by writing a single line through this HDL language, so I can convert this through a circuit, a big circuit. Getting my point? So you can see there is nothing like I need a number of kids, more people are required, more timing, bug fixing and all. It's just like code, something is missing, some error, okay, I'm not getting proper result, I will change that, I will write according to my truth table, I will write the code by seeing this truth table. So I will what I want, if this is this, I will, what I will do in a lookup table and all, if these two are there, then I will put this as output, if these two are there, I will put simple logic program, I will write here in my HDL. So this will convert to what? Automatically he will convert this to what? He will convert this to a schematic. Getting my point? Then this schematic, this netlist is converted to binary, and that binary is dumped to your FPGA, and FPGA start working. Okay, these many IOs I need, these many input, these are the output, this is the processing. So this is how we are going to design. It's called as a reconfigurable. Okay, you can see this complex circuit. Can you see this simple code I will write? So the huge, you will generate a netlist of you. If you go to block by block, so what is there in that block? You have some adders inside, go some AND gates. What is that AND gate? Again the same. When you go inside, again the same thing, because through trainer kit, by using this AND gate, I can't design this much complicated circuit. It's too difficult for, as I told, the timing, then bugs, then mistakes. Getting my point? But with the help of this HDL and all, we are using Verilog HDL and VHDL languages. So with the help of those languages, easily I can write a code, I can develop this complex circuit and all. So if you see this, as I told, that difference is already, you know that this is a predefined architecture, and here I can design my own. Even I can design this controller on my what? On my FPGAs, because this is a programmable. I can program, I can design according to my wish and will, from basic circuit to a complex circuit. You can say that. Okay. So how this controllers are designed? Again the same thing. These are designed with the help of FPGA, then with the help of ASIC chip it is dumped, and so many things is happening. So ASIC you can say that ASIC. Okay, we are not going to ASIC and all. Okay. So next, so what might be difference? Like you can see that C programming, how your C and HDL are different. So because as I told that both are programming language, right? One is both are programming language, but what is the difference? One is for, it's a software programming language, that is a C, and one next is what? HDL, that is a hardware. In C programming we are using a ready-made architecture and we are writing a code, but when it comes to HDL we are using a what we are designing our own architecture, we are designing our hardware. If you see these two codes, so can you see what is the output? You are writing the code here in C, right? So how you are writing? For example, I want to have addition program. So at that time what I will do, I will use some data variables of some data type, like I took a int, then what is this? I stored a into this memory, 10 into this memory, and I store 5 into this memory. Then I tell that C is equal to a plus b. What is the output? I will print that output. What is the output? I will print a, that is 10. I will print b. So that is how you are writing the code. But the thing is, this is general C, but when it comes to embedded, you need to see the data types. Data types are very much important, because when I ask some basic question, even for developers and all, they will get stuck, because the memory is, they haven't understood what do you mean. See, most of the time they will tell int is 4 byte, int is 2 byte, char is 1 byte. That is not the case. But why it is, how we are going to store? See, in general you could write, okay, that is fine, but when it comes to embedded system, when it comes to controller side, memories, all those things are important. Okay, fine. This is how we will write code, like, okay, I want to add this. So next, so similarly I can write a code. This is your HDL, like HDL language. So how I will write the code if I want to add two things? So what I will do is like I will write, like you can say 4-bit 100 to A, then 001 to B, then I will give this C is equal to A plus B. So what is the output? He will give 15. Similarly here also you can say 10 plus 5, 1010 A or 5. You can say, I will also think that you are getting a 15 over here. Getting my point? So next, so now what will happen here if I give this? Are you getting my point? I have initialized the memory A, B, C. Then I am telling that C is equal to A plus B. Then A10, B5. So do you think that I will get a result for this? Because what I am doing here is, I am initializing the memory and I am adding the memory, sorry, I am declaring the memory, but it is not initialized. Can you see that there is no value initialized here? So what I am doing here is, without initializing, I am trying to add two different variables. Getting my point? So then I am storing this C, then I am printing 10, initializing A, initializing B, then I am trying to print. So this definitely this will not work. If it is working, I am not getting a proper result. I can get some garbage value, I can get some zero values. Getting my point? Because before this you have used this instruction. It's a sequential, right? Your C programming is what? It's a sequential language. It's a line by line. So it will start from here, it will execute. It's a sequentially. Getting my point? It's not, it will not execute like parallelly and all. It will execute sequentially. So when it comes to here, it will execute this instruction, then he will come to here, he will execute this and all. So I will not get a proper result. But next, when you write same thing, see, previously what I done is, so A, B, then C, A, B, then C. But the thing is, next what I have done is, first C, I have used this A, B, and C. Then I have initialized the value. So definitely this will work, because this is what, that is what I'm telling. It's not like like your C programming. It is running in a sequential, but this is running in a parallel. Getting my point? This is not a code where you are writing for your architecture. This is, you are designing your own architecture. That means parallelly. You can run the process in concurrent. You can are you getting my point? This will work. This is what the advantage. Wherever you place this, so it will work accordingly. That is what the difference between your C and HDL language. So if you see here example, so I will take the microcontroller for an example. Then I will connect LED for this. I can connect a LCD for this. I can connect a 7 segment for this. Then I can connect you can say DC motor for this. I can connect a DAC for this controller. I can connect again LED, you can say IR, or what. I can connect like these all are what, output devices, right? Output, output, that is what I'm sending some information is blinking, I'm sending some displaying, displaying, I'm sending rotating, I'm sending, so converting digital to analog and then feeding to some buzzers or some speaker or wherever you want. So the output. So but next thing is, even I can have some input device like ADCs, so analog values, because nowadays IoT, all our sensors are connected, those things are converted to digital, because your controller or processor will be doing digital processing and all. So it will convert, it will do that input. Then similarly you can say analog input, then n number of ADCs. Getting my point? You can connect n number of ADCs. Okay, fine. This is how you are connecting some other devices. Okay, you are connecting with the memory. Okay, because you want to store the value, some EPROM or PROM, EPROM, whatever it is. So this is how you are doing. Okay, similarly when you place this FPGA will also do that. Getting my point? Your controller also do the same task, and the same task can be done with the help of FPGA. Then why FPGA? Okay, already controllers are available and the cost is also very less. So why again we need to go for the FPGAs? Why simply I can use the controller? But if you see the difference, the challenging thing is there. So if you take the example of your controller, can you do all this parallelly? all this parallelly. At a time I want to read, at a time I want to blink, at a time I want to display, at a time I want to display here, at a time I want to run a DC motor, at a time I want to convert that digital to analog signals. I need to send here, I need to work with all this. It's not possible with your controller, because as I told, that controller works on a sequential, like C programming, embedded C, sequential. But when it comes to FPGA, you can have a parallelly at a single shot. You can have working with all these devices. You can at the same time, getting my point, at the same time, parallelly you can run all this parallel. You can display out, you can show the blink the LED, you can display parallelly. So all this process will run what, parallelly in your FPGA. That is what, because I will reprogram for this. That is advantage. The next advantage is a parallel. So parallel execution of all time at a single shot, I can execute all the programs. That is where these FPGAs are under boom. So nowadays, as you know, that as I told, IoT in another 5 years, Internet of Thing, artificial intelligence, data science, everything will be like everyone are using to that this one. The thing is, so FPGAs are very they will play an important role in your future. So what is that important role? Important role is because n number of data you are gathering from different sensor. At the same time, you can display it, you can process it. Getting my point? So many things are there. That is where the FPGA is very important, and having a more advantage over other controller or a PLD devices and all. So what I told, the big advantage for your FPGA is a parallel process running. It's running concurrently, and reconfiguration. These are the two main big advantage of your FPGAs. Okay, what is inside FPGA? As I told, that you can see this. This is your FPGA. So you have something called, as you can say, these are the programmable interconnect, where you can connect from this CLB to this CLB. Interconnections are there. And then you have something called as a programmable logic block. This is your CLBs and all. Then you have something called as a IO pads. You can say IO blocks. Again, these also can be programmable. Okay. So I can program. See, if you take embedded system, so pins are fixed, right? If you take any embedded system, one is fixed for ADC, another fixed for DAC, another is fixed for some I2C, SPI, then TX pin, RX pin, UART, and all those are like fixed. But in FPGA, I can program this. I can make this pin as an input, I can make this pin as an output, I can make this pin as active high, active low. Okay, getting my point? And I can have as like sleeve rate also for this. So I can give the maximum output, whatever output I want. I can have this pin for like 1.3 volt or 3.3 volt or 1 volt. I can change this, voltage levels and all. Getting my point? But the thing is, here if you see this FPGA, it is a non-volatile. Getting my point? Non-volatile in the sense, what, it is a non-volatile memory. So all this, once the power goes, so he will forget all these things, whatever I designed, and whatever AND gate I have designed, whatever OR gate or adder or multiplier or my controller I have designed, so he will forget. So that is what it's a non-volatile. But the thing is, what we will do is, we will have like you can say external flash memory in this. Okay, so where we can store that information, and whenever you switch on, it will configure that logic, whatever design from your flash, and you can work with this. Okay, this is what all inside your FPGA. And if you go this, as I was telling, that see, it look like a matrix, right? Matrix, some rows are there, like 3 rows, row 0, row 1, row 2, and 3 columns, column 1, column 2. So you can see, so what is there inside your FPGA? You have three main modules, you can say. So one is a CLB, that is a logic block, configurable logic, where you can configure, you can design your own circuit. Then you have an interconnection. This is what SMs, switch, you can say switch matrix. You can say this is the switch matrix, where you can interconnect from one CLB to another CLB to IOs and all. Okay, then you have like these are what, these are IOBs. IOBs are nothing but IO blocks, or you can say IO pads. Okay, so you can see it's the architecture look, it's like a two-dimensional arrays. This 2D array, right? Rows and columns, it look like a 2D array. Fine. So that is what I was telling, that SM switches again. So you can see so many interconnections are there, so it will connect to each other with the help of your switches and all. CLVs, logic block, IOBs, IO pads, and even you have so many different architectures like symmetrical array, row based, C of gate. So many architectures are there. This is the same CLB configuration, already told, right? Like I was digital logic, input output, then the directions and all. Okay, CLBs, SBs and all. Okay, so if you see this, if you see the CLB, so now just we will go inside the CLB. What is there inside this CLB? So if you see this inside that CLB, you have something like this. Are you getting my point? You have something called as a lookup table, then you have a flip flop, then you have a mux. Okay, this is what is present on your CLBs. Lookup table, then a flip flop. It is a flip flop and a mux. So now we will see that. So as I told that your CLB is having lookup table, flip flop, mux and all. So how exactly it is working? So we will give the input to where? Input to what? Lookup table. So whatever bit streams are available, so that is stored where? It is stored in your lookup table, that AND gate. For example, if you take a AND gate, so how many possible addresses for that AND gate? Like 00, 01, 10, 11, like 4 different values. And get 00 means 0, so I will have 0 in one this one. It's like a RAM, you can say. LUT is something what is a it's like a RAM, you can say, lookup table. So where we are going to store some values. So if it is here, then the value stored at this place is what? 00, that is 0. You can take the example of and get here. Okay, you can take AND gate or half adder, whatever it is. So if this is what these are stored, these values are stored in your lookup table. You can see when it is 00, so he will send a value 0 to where? 0 to your mux, or you can say clock. When it is 10, what is the value? When it is 01, what is the value? When it is 11, what is the value? So these values, if you say example of here AND gate, as I told, 0 is two inputs, right? 00, 01, 10, 01 and 11. So what will be the output? This output is loaded to your LUT. See here, see that is loaded to your LUT. So if this is 00, then I will send a 0 to here. If it is 01, I will send to 0 here. If it is 10, I will send 0. If it is 11, then only it will having that 1 will be there, that will be sent. So this can be sent to output. Either I can send this directly to the mux, or I can send with the help of some flip flops where we will give the clock and all. So as we know that, what do you mean by flip flop? So it's a delay bit, and even you can design so many circuit with the help of flip flop also. Getting my point? So this number of input is there, this is the output. So based on this is what it is there in your LUT, that is what lookup table. And then that is what CLB, what we are, that is what CLB is inside this CLB. So we have these things: lookup table, then flip flop, and then mux. So you can see either you can give the output from the lookup table directly to the mux, or through this one. So how mux is going to select? We have some selection pins here. So we are going to select whether I want output from this pin or this pin. Selection pin 0 means I will get the output from here. 1 means I will get the output from here. That is how that CLB is. Okay. And here for configuration this, we are using Model Sim and the Xilinx softwares to generate the that is what the tools we are using to write the code and generate a bit stream and all. Okay. So LUT is what? It's a RAM with a data width of 1 bit. You can say that. Okay. The contents are programmed at the power. And okay, if you take the another example. take the another example of this what you can say a 4-bit 4 input AND gate. So how many inputs are there? 4 inputs. That is what I am giving to LUT. Getting my point? 4 inputs. So what I am doing is I am giving some 4 inputs. So what are those input like 0 0 4 0 0 0 0 1 0 0 1 0 and all these are the inputs I am giving over here. So what will be the output for the AND gate? AND gate is what? All should be 1, right? That is here. Other than this, if all are true, then only I will get the true output. If any one of this is false, then I will not get. So what I will do, this is returned to where? It is returned to your LUT to achieve the functionality. And what is there? So everything is, so this is having some address like 00 is the address for this. You can say 00. So what you can say from here, if you want to start from here, 00 is the address for this, 001 is the address for this. Are you getting my point? Like if 0000 is there, then he will go to this address, okay, and he will send. If it is 0010, they go to this address. Are you getting my point? So how it is designed in such a way that he will get the information from your lookup table, and he will send either directly he can send to the mux or through a flip flop. Getting? So how we can configure? We can configure that if it is a bit is 0, then what is happening? If bit is 0, it is going like this. So for example, a thing that this is the value I have selected 1001, and what is the output? If I select this here, the output he will go to that specific address. Okay, 0 is there, so 0 will send here. Okay, and here this value I will select. Similarly you can have n different this also. If it is 1, so what we can do, we can pass the value from here and you will get the output. That is what available in your that LUT, the bit file configuration. You are configuring all the bits in your LUT, and mux will be there. Based on that, selection will be happening and you are getting the output. So you can see this is the diagram. You can see x XOR y XOR z and all those things. So you can design your own this one. And when it comes to schematic, so you can have a different schematic, like RTL schematic is there, technological schematic is there. When you see RTL schematic, for example, in your HDL you have written this code. What you have written? Y is equal to A and B and C. Then what is happening? So he is going to convert this to some schematic. So what schematic you are getting? Whatever you have written, like AND gate you have written. Na? So he took AND gate A, B and C. It is converting it into same AND gate channel. That is called as a RTL schematic. But when it comes to technological schematic, he will not convert to that gates and all. Getting my point? He will convert like this, like LUT. So you can see here, you can see here LUT is there. Getting my point? So he will convert to this, and what is there inside LUT? If you see that you have a gates, you have expressions, you have a truth table. So here tool itself will give you the options here. Getting my point? Then K map, Karnoff map and all you studied in your, because this, see what we studied in your academic, really we are using in industry. See, subjects are good. What we are learning in our academic subjects are good, but the thing is, we need to understand the subject and we need to match with the industry. Are really we are using this K map in the industry? Are really we are using the truth table in the industry? Are really we are using the Boolean expression in industry? Are really we are using the gates and all this connection? These are very important, because if you know the concept, you start loving to the subject. Getting my point? And you can design your own architectures and all. CLBs, you can see that inside your this one, it is like this. When you click, again you have CLBs, interconnection and all. Again, when you click on the CLB, you will get the diagram, how exactly the circuit is there, how exactly it is connected. So all this information you will get. Same. Suppose if you have like 3 inputs at that time, what you need? For example, I want to interconnect with, like, I want to make 2x2 FPGA, where I will use some 2 different blocks, CLB blocks, block 0 and block 1. So at that time, what I can do, I can take like 2 input from this block and 1 input from this block, and I can you can say that I can merge it. I can interconnect from one block, one CLB to another CLB, because as I know that CLB is having what? Lookup table, flip flop and mux. The output of one CLB can be connected to input. You can see that this is how this is designed. So this is designed into 2 different set, right? Two like you can say 2 half adders. We have designed 2 half adders. So input 2 input from this and 1 input. That is what I am doing here. 2 input in lookup table, then that is given to marks. I selected this one, so instead of here I'm getting the output from where I'm getting the output from flip flop, then this output, this output of this is given to one more CLB input. Can you see this? Now this is indicating, oh, that is what output of this is given to here. Then next third input I have taken here, then again same thing, lookup table, then flip flop. Here instead of 1 I have selected 0. Now I'm not taking through D flip flop, I am taking directly from here. Getting my point? Why this D flip flop you took here? Because I want a delay, because I want to have both the things parallelly. Getting my point? Again, the big theory is there for the delay circuit, why we are using that delay, what is that flip flop, what is that clock and all. Fine. Similarly, when you see that SMA, that switches and all, so it is internally connected like this through some SRAMs and all. Getting my point? If I load 1 to this SRAM, then it is connected. If I load 0 to this SRAM, this is disconnected. This is how it is connected internally. Similarly, see here, the thing is, now we know that what is FPGA and all. Now in the market you will get so many different boards also. Getting my point? Low cost boards available where you can practice, and even you have onboard peripheral, so many onboard peripheral like 7 segment dip switches, LEDs, and GPIO pin, see your memory card, everything there. Again, what you need to read, you need to write a logic and you need to interface with memory card. Write a logic, you can interface with your serial port. Write a logic and interface with your audio ports, video ports, a 7 segment. You can do that. Getting my point? Based on your requirement, these are the best training kits, low cost, available in market, where you can start working on this. Fine. Okay. So as I told that volatile, right? Volatile. What? Oh, this FPGAs are volatile. Volatile in the sense what? Volatile means once power gone, then everything is on. That's why again we are using something called as a PIC and all for some flash memory. So if you see this onboard SPI flash will be there. So what we are doing through USB, we are coding this, and here option will be different. Like you can have a serial communication, or you can have SPI communication. So what you can do, you can have an interface between this, and you can work the FPGA like onboard flash, and then you can program whenever you remove the power. For example, I have programmed here. So if it is a volatile, if I remove the power, my program is gone, right? So I will use some flash memories and all. So at that time, when I power it, so this will I will write the code. It is working. When I remove the power once again, then the code whatever there, it will load from your flash to FPGAs, and you can start there. Still your code is available because you have a flash. Nowadays, see, so many things are going into this one. The embedded controller into this, the embedded DSP processor into this, the embedded flash, the embedded RAM. So many blocks are there. They have embedded on this. So now, so the thing is methodologies. Methodology, how we are going to work on this. So first thing is a requirement. So we need to take a requirement. What is the requirement? How many modules you are going to connect? What is the data? For example, if you are designing a comparator circuit, so you need to have like I need a 4 modules where I am going to compare this. Okay, I will check that. Okay, these two number, if any one of this greater, I will take that number to this position. In this greater one, I will like 1, 2, 3, 4 is there. So 1 and 2, which is greater? 2 is greater. 2 will come here. 3 and 4, which is greater? 4 will come here. 2 and 4, which is greater? 4 is greater. So output will be 4. This is how I am taking the requirement first. So with that requirement, it can be a requirement of your lightning signal, counter, timer, comparator circuit. So first you need to understand what exactly you are designing. The next thing is, based on that requirement, you need to design the architecture. Getting my point? You are designing the architecture, like you are designing, you are using gates and all. As I told that you are not designing this, you can do that. There are different techniques for that. So you are writing a HDL code where it will convert this to the schematics and all. You are writing some truth table, this also you know, and how with the circuit diagram, K maps, you did all this by this directly. See, no need to by heart and all. With the help of this K map and all, you can design your own circuit, own designing and all. Getting my point? So this is fed to where? This is fed to your lookup table, where based on the input, the lookup table will give the output to where? To output to your D flip flop or mux. So architect, then behavioral simulation will come here. So what do you mean by behavioral simulation? That is where I need to check 5 plus 5 is 10 or not. That is what my result. I will check two things. Okay, this is 1, this is 2. What is the output? This is 1, this is 4. What is the output? That is what I am checking the behavioral simulation in this. Getting? Similarly, synthesizes, like I can check the are you getting my synthesis? As I told that it is converting that HDL code to some logic gates, or you can say lookup table. As you see this is a lookup table. So two different ways, na. One is what RTL, and another is what you can say that synthesizes. That is what here I explained, right? Technological schematic and RTL. This is RTL as it is, whatever you are written as it is, it will convert. But technological schematic, it will convert to that lookup table like this. Getting my point? You can see here. You can see here, this is a lookup table he has designed in such a way that he converted that to a lookup table and all schematic synthesis. Once this is done, then you need to have a UCF, that is a user content. For example, now you have written the code, you have tested, you have simulated on your software. Now I want to dump the code into my hardware because it should work, right? So at that time, pins, the pin numbers and all, that UCF file is given by whom? The UCF file will be given by your board supplier. He knows that which pin is connected where and according to those pin, what you can do, you can design your circuit. Getting my point? You can design, I want to write this one for 7 segment and all those things. Fine. So I think because of this short time interval, I will try to cover fast. Then this is the methodology what we used. First we got the requirement, then we have designed the architecture. Getting my point? Then we have written a code through HDL. Then we have done the behavioral simulation, checking of that whether it is a code is working proper, or if it is not, again I will go back to the architecture. I will design the architecture. I will check, okay, now I'm getting 1 plus 1 is 2, 2 plus 3 is 1, whatever it is, 0 0 is 0, and all those things I will check. Okay, I will check here. So because I need a result here, then I will synthesize. That means I will convert this to some architecture and all. Then implementation. Getting my point? Implement it. So then this implementation is like given to time analysis. What is time analysis? Here you can see exact time. If it is 1 nanosecond, I need to get the output at 1 nanosecond. Or else what I will do, again I will go back to my code. I will check where I am lagging. I need to check this. What is the problem? Why it is getting delayed? And according to that, I need to fix it. So then this stream is generated, and this bit stream is dumped to where? It is dumped to your IC. Getting my point? So you can see the summaries also. You can see the summaries like how many gates, what is the timing, all those things are available here in your this one tool. So dump and work, this is what your code is. The other component, as I told that there are some special component also. Can you see these are the CLV? This CLV, again, if you see here red color and this one, these are what? Some special components. So you can see RAM block is there. Here it is a DSP block. If you see this DSP block, and if you see here some RAM blocks are there, DSP is there, RAM is there. So these are some of the special FPGA functions. As I told, with FPGA, CLB block is there. That is what a soft core. Even you have a hard code on that, like internal SRAM, a multiplier, DSP, logic analyzer. So many things we can have on on this hard coded. If you see this a typical FPGA, so this here CLB blocks are there. With that, again you have something called as a DSP. What is DSP? You have multiplier, and you can say multiplier and adder. So all those things are there here. So ready made, because DSP is most powerful when it comes to higher end application and all. So if you start, as I told, that 48 cross 48 multiplier, if I waste time to design 48 cross, so all pins are gone and all CLVs are used. To overcome all these things, they have designed some special you can say these are the things, special function like SRAM is there, internal. We are no need to design SRAM. Some ready-made multipliers are there, DSP blocks are there. Then embedded, like you can say dump controller. If you have some application of your controller on FPGA, that is there. Okay, these are like so many things are there. Then buffer. Okay, interfaces, as I told that. Okay, so this, and if you see your example of your mobile phone, so if you think how your mobile phones are designed, okay, so that can be having a processor Snapdragon. So if you see inside the Snapdragon, you have Wi-Fi, you have GSM module, you have LTE module, you have Bluetooth, you have GPS. Okay, but if you see this LTE module, what is there inside? Inside that LTE module, we have something called as a stack. And if you see what is there in the stack, it is a physical layer. What is there in that physical? Again, it is a transmission and reception. Like if you see the transmission chain, what is there inside? It is the OFDM. What is there inside that OFDM? IIFT. If you see this FA50, getting my point, transmitter side, receiver side, IFT, this already you learned this filters and all in your academic, but understanding, see, if you open that FFT inside, so what is there inside? Again, this butterfly diagram done, na? All exercises. This is a logic. Okay, if you open this this one, so then what is there inside? Again, it is a multiplier. Can you see? Adder, this one multiplier. Getting my point? If you see what is there, multiplier, again adder, full adder. Okay, if you see over full adder, what is there inside? Again, that two half adders and all, whatever we studied. Getting my point? So this is how the architecture is. Getting my point? From where to where we came. Getting my, if you go inside this mobile phone, so again we are doing the same thing. We are writing a logic. Getting my point? Okay, so what are the advantage? As I told that we can do anything, like I can design my microcontroller, supercomputer, I can connect 1000 LEDs to my FPGA. Getting my point? That is not possible with your controller, because of limited set of IO pins and all. But here you have huge number, so then it is super fast. I can go with a gigahertz speed. I can design my own this one. Then programmable, there is a big it's not a fixed, we can program, reconfigure. Then parallel, as I told that parallelly, 1000 if you connect 1000 LEDs, 1000 LEDs at a time I can control. It's not sequentially what we are doing in the C programming and all. Okay, so many things are there. And if you see, the disadvantage, expensive. So it is somewhat expensive, but nowadays they are reducing the cost, as well as they are adding controllers, all those things. I don't know in future and all, everyone will switch to this FPGAs and all. Then it will take high power. This also they are working on this, trying to reduce the power. Intel and all, they those guys are working on this. So then volatile, as I told that already, flash memory is there inside that. So then high pin FPGA, as I told, that is okay, complicated, many traps, so many things are there. Okay, then next thing is SoC. What is SoC? As I told that SoC is what? System on chip. As I told, system on chip means everything is there on the chip. You have FPGA. In that FPGA you can have a processor, ARM processor, you have DSP. That is where the FPGA is going like somewhere in other direction, because it is having a power of your ARM controller, it is having a power of your DSP, it is having power of FPGA. You know what, where it will go. So if you see the example of on-chip, as I told that onboard peripherals and on-chip peripherals. What are onboard peripherals? Like 7-segment, hex keypad and all those things. But on-chip peripheral, RAM, ROM, IO ports, that is on-chip, right? That is also important. So different architectures are there. Like ARM is there. Then even you can see that Innovatech solution, they have a LPC214. It's a good board they developed. So you can see this. This is the chip. Okay, so onboard peripheral, what is the chip? This chip can be designed. This is the chip which can be designed based on, see, the chip this chip can have many features, right? So many things are there, but for my board I don't want all those things. What I will do is I can design according to my requirement. I have only hex keypad, I have pins, so I have you can say potential analog, temperature sensor, buzzer, then LCD, 7-segment, then motors, then even JTAG, serial port. These all things I can, what I can do, I can configure through that FPGA. And what is there? So you can see this. These are, as I was telling, that FPGA controller is having fixed pin. So you can't use this pin for this. You can see this pin can use only for your GPIO or AD and all. But in FPGA you can design your own configuration, because other pins can't be used. Getting my point? I can use only some required pin based on the architecture, and I can connect. Other pins is waste for me. I can't use for my application and all. But when it comes to FPGA, so this was the internal architecture, what I was telling about the chip. Inside this chip, if you go, you have this all things you can design. As I was telling, you have like you can say I2C, SPI, UART, then a processor, ARM processor, the buses, AMBA bus, APB bus, AHB buses, so many things are there. Getting my point? Onboard peripherals, block diagram of your controller. Okay, similarly one more board from Innovatech solution, that is a Cortex based LPC1768. So if you see, so many peripherals are there. Again I can design this controller also, because this controller architecture is again different. Can you see this? So there might be in that RAM size is different, ROM size is different, IO ports are different, then so many things in that. You only I have one UART, but in this, so I can design all this in my FPGA. Getting my point? Because I will see again that I will see what is required, what are the peripheral, how many pins, what is my what is the functionality of board, what is my application, what I want to do. So here it is a fixed, as I told that this guy has developed the architecture. I need to read this architecture, I need to read this instruction set, and accordingly what I need to do, I need to work. But FPGA, I can design, customize, reconfigured. Getting my point? So this is all things, so many things. And even when you are reading that, see LCD, if you want to make LCD, definitely what is LCD? So 16x2, if you take the example again, if you go backside and see, there is something called as a controller. You can design your own controller for LCD and all. Getting my point? So timing diagrams, all this you should learn. And you can see huge number of applications because of this parallel computation, digital signal processing, medical, computer, speech, so many things. These are the SOC. As I was telling that SOC is there on that system on chip, means you have, see, you can see this yellow color area, and this yellow color area is what is a programmable, which is a FPGA. And in the complete FPGA, even there is a hard code, as I told, a hard core, soft core, hard core. Soft core is nothing but I can reprogram it, whereas hard code, it is a permanently ARM Cortex architecture. I have hard coded, I can't change it, because the thing is, whenever I need to design, I will design. Whenever there is a requirement of controller, again I will not design, and I will waste this CLBs or RAM or blocks and all. I will use already ready things are available. This complete things is available on your chip. That is a system, complete system is on available on your chip, hard coded. ARM Cortex processor is hard coded onto the chip. I can have dual, even DSP processor also you can hard code. Getting fine? So differences and all, and you can see. And okay, some application like it, automotive, motor control, power window, see, so you can design customized. So wireless communication, telephone, answering machine, network, these are all application in communication. Military application like target, guidance, navigations. Okay, medical field applications, different ICs you can see, like these are like two famous, Altera and Xilinx. As I told, this is having their own FPGA like statics and all, and this Xilinx have like Spartan and all. This is acquired by Intel, and this I think it's they are acquired or acquiring, I don't know. AMD is acquiring this company and all. So there are different FPGAs. The difference in the sense, difference is the RAM, block RAM, number of block RAM, logic cells here, Arctic 7, Vertex, Spartan. So many different FPGAs are available. So what might be difference? Even they have a architecture like 3,52,000 logic cells are there, 4,80,000. So you need to see these features also. What is the IO voltage level? Like you can see, this will support for 1.2, 1.3, 1.5, 1.8, 3.3, and how many IO pins, 600 pins, 1200 pins. It depends upon your application, what application you are developing. So all these things are MBPS, DDR, so many trans receiver, so many things are there. So applications and all. Okay, so the thing is career and all I was telling, right? The time is less, but anyhow, what we can do is, what is required in, okay, this was the thing what I was telling now. See, nowadays it is a boom of IoT. Getting my point? Artificial intelligence, then data science and all. But all those things, when it comes to embedded system, these are the things you need to learn. So you need to have a good knowledge on your devices. You need to have a good knowledge on your language, whether it is C, embedded C, data structure. See, I give the training, these all trainings I will give for corporate as well as embedded. But corporate guys, they will not take a full package and all. They are specific to some this one, because when I trained for this Collins Aerospace and all, they were fixed to board bring up. Board bring up in the sense, they used to make some accelerometer on their helmet and all. Something they are doing, they have designed their own processor. So they want to do it from scratch, like they want to put their own custom bootloader, then kernel, then root file system, and they want to write some drivers and all. They took that training. Similarly, these are the training I can provide for you, because I'm working as a consultant. But what you need to learn is, first thing is a programming, any programming language, and most important is a C when it comes to embedded system, embedded C, and when it comes to your FPGAs and all, Verilog, that is a VHDL or Verilog HDL is important, and MATLAB and all, so image processing, audio processing, even you can do that image processing in Verilog also. Then next, coming to controller, any one controller, see so many, I know because I can work with any controller, but you should learn one controller, but to architecture and all, because almost all controllers will be same with a little difference. Then processors, so to start, see I work with Davanci, Texas Instruments, so many processors and all, but for you guys you can start with the BeagleBone Black and Raspberry Pi, because these are the open source tools available in market, where you will get a support also. But when it comes to Davanci and all, you should be good at this one, architecture and programming. Then DSP, you have fixed point, floating point. Then Linux, as I told, that system programming, shell scripting, IPCs, thread. These are the important. What I'm telling, these are the required things in market now. 4 or 5 years, no. If you are, if you learn all this technology, definitely you are fit to market. Then autos, free autos, when it comes to real-time operating system and all. Then IoT, you can start, see IoT even you can do with any of the controller. I'm telling na, Stellar is there, there STM is there, Sitara is there. But for you guys, what you can do, you can start with Arduino. Then Arduino is just to understand the hardware and all, but this is not preferable in industry and all. They will not do this. But the thing is, where you can learn the devices. This device you can connect to Arduino and you can learn. Then Raspberry Pi is open source. You can have a sister, like it's a SBC, you can say, simple computer board. It work like a computer. And some of the Wi-Fi tools are there: Zigbee, Wi-Fi, Bluetooth, IO, so many. But ESP and Node MCU, you will get a lot of support here. You can use that. Then communication protocol is very much important, because from communicate, as I told, that if you want to communicate between two different devices, you should learn all this: UART, I2C, SPI, CAN. Okay. Then MATLAB, like as I told, that it is like simulation, more towards simulation side, like image processing, audio processing, video processing, Simling model, or else you are writing a battery management before going to hardware. You can check all those this one in your software. So this is all about FPGA and this one. So I hope you have understood. Applications are there, but time is already done. So ADAS, automotive driver assistive system, where the driver can have a, you can have a camera there. So the driver automatically, what camera will do, he will capture your eyeballs and all, whether your eyes are like you are blinking your eyes, or based on that he will control your vehicle. And even if you have a camera outside, so he can see the signboards. Okay, then pedestrian crossing and all, zebra crossing will be there. And even automotive, like your car will move automatic based on the tracks and all what is there on your roads. So many things in ADAS. Then encryption, decryption also you can do here, cryptography. Then image, audio processing, video processing also. So n number of applications are there. Okay. Okay, this is all about FPGA. I hope within this short duration I have given a flavor what is FPGA and all. Saif bhai? Hello? Saif bhai, I am done with this.
Asif?
Yeah.
Nothing. This is Munib. Is it done or anything you want me to add?
Yeah, Munib, nice to hear that. Saif bhai, Munib bhai is a developer for this VLA, FPGA boards and all. And he worked for ISRO, DRDO through clients and all. So the audience, if you have any question, any doubts on this one, so he's the best guy to answer you guys. Any question on FPGA and all?
Assalamu alaikum.
Walaikum salam.
Zamir here. I'm from the IT security background. So I want to learn regarding the IoT. So purely my work is all about the auditing part. Okay. Now tomorrow to keep myself upskilling. Okay. And I want to know what IoT today, tomorrow going to use in coming days. Okay. So how can I get a knowledge on, especially on IoT? Yeah.
See, IoT is simple thing. IoT is that is nothing. Name itself is telling Internet of Things. The devices, whatever device is there, when you connect to internet, that will become an IoT. It can be a small sensor to high-end sensor. It can be a small like a temperature sensor, pressure sensor to industrial oriented sensors. So the main challenge if you want to learn IoT, first thing is you need to learn any one of the controller, where you will get the information. Any controller, you can read the information from that IoT, and you can process it and you can display. The next thing is towards cloud side. So then the data, whatever data you are read, whether what you are doing with the data, whether you are having the data at the same place, or you want to have a remotely access of the data, or remotely controlling of the devices. So automatically, so one time manually also you can control automatically. So for that at that time, again you need to go with the wireless devices and all, and some open source like ThinkSpeak and all those clouds are there. You can start with that. Then even there are some servers where you can buy and you can design your own server. As I told that even through that Raspberry Pi and all, if you want to learning level, I'm telling you, without spending huge amount and all, so you can make your own Raspberry Pis as your cloud and all, and you can get the value from one controller and fed to your this one. And Raspberry Pi is also having that wireless this one. So Ethernet connection is also there, Wi-Fi connection is also there, where you can connect to through your hotspot or something through your internet, or your office internet, and you can see that remotely. So there, the thing is you need to understand the devices, sensors and all. Then you need to have good knowledge on the controller. Controller in the sense like controller or processor, C programming, Python language and all. The next thing is a cloud. But when you go to cloud and all, again the languages differ because data. IoT means it is a huge data science, artificial intelligence will come there. So there what JavaScript you need to learn. If you are working on the cloud side, then you need to have SQL queries, because database and all. So you need to get the data, you need to store the data, all those things will come into picture. And when it comes to GUIs and all, graphical user interface, so you should have some knowledge on your that HTML or some programming language. So this is how you first, the area is big. So you first need to decide whether you want to work on the only cloud side is almost software. But when it comes to devices and all, it is again a controller and some devices which is connected to internet through Wi-Fi or through Ethernet cable. You can tell that. I hope your answer is you cleared this answer.
Yeah, shukriya.
Okay.
Hello, am I audible?
Yes.
Assalamu alaikum, sir. Okay, I just wanted to connect with the person who said that he has worked with FPGA programming and all. Can you please tell the name of the person once again?
He's a Munib Rahman. You can talk. He's online. You can talk with him. Munib.
Okay, I'll personally text him. Thanks.
Okay. Okay.
And sir, do we get the presentation as well for this?
No, you will not get the presentation. See, if you want a training and all, or if you want any further this one, you can contact to MFIRD.
Just a minute, Asif.
Recording will be shared, inshallah.
Okay.
This recording will be available.
Yeah. Also, I've just shared my personal email ID on the group. So if anyone wants to connect, they can connect via the email for any specific questions. I think I saw a lot of them were asking questions regarding ADAS, cryptography. So if anything specific is there, you can connect me on my personal email ID, which I have posted it. It's munib.rahman@gmail.com.
Thanks, Munib bhai. I have taken a screenshot of the chat. I'll get back to you. And I'll take this for Asif bhai as well.
Okay. So, Saib bhai, can we conclude this? Like, can we? Saib bhai, can you hear?
Sure, Asif bhai.
Okay. Thank you.
Jazakumullah for this very nice and interesting and very informative session. Inshallah, people will continue learning and maybe implementing also FPGAs. So thanks to all the audience also for participating.
Thank you. Assalamu alaikum.
Okay, Jazakumullah.
Thank you. Jazakallah.
Assalamu alaikum.
Alaikum.
Wa alaikum salam.